Picture this, a fleet of satellites orbiting Earth, their sleek surfaces glinting in the sunlight as they silently monitor the planet below. Suddenly, a missile streaks across the sky, launched from a hidden location thousands of miles away. In an instant, a beam of light shoots from one of the satellites, intercepting the missile mid-flight and neutralizing the threat before it can cause harm. This isn't science fiction, it's a glimpse into the future of space-based defense systems, a future that's closer than you might think. Welcome to a world where the final frontier isn't just about exploration, it's about protection, security, and the balance of power on a global scale. Today, we're diving into 25 in-depth predictions about the future of space-based defense systems, exploring how these technologies could reshape the way nations defend themselves and secure their interests in an increasingly complex world. From orbital platforms armed with cutting-edge weaponry to swarms of autonomous drones patrolling the cosmos, the possibilities are as vast as space itself. But why does this matter to you? Because the decisions made today about space defense will ripple across generations, influencing everything from international relations to the safety of our planet. So buckle up and get ready to explore the future of defense beyond our atmosphere, where innovation meets necessity and the stakes are higher than ever. Let's begin. Now, let's take a closer look at the first prediction: orbital defense platforms. Imagine a network of permanent structures orbiting Earth, armed with advanced weaponry designed to detect and neutralize threats before they can reach their targets. These platforms would serve as the first line of defense, offering unparalleled speed and precision in responding to missile launches, cyber attacks, or even space-based threats. Unlike ground-based systems, which are limited by geography and atmospheric interference, orbital platforms would have a global reach, capable of monitoring and protecting entire regions from a single vantage point. One of the most exciting aspects of these platforms is their potential to integrate cutting-edge technologies already in development. For instance, directed energy weapons like high-powered lasers could be mounted on these platforms to intercept missiles or disable enemy satellites in seconds. Similarly, advancements in artificial intelligence could enable these systems to operate autonomously, making split-second decisions without human intervention. Current projects such as the United States Space Force initiatives and Russia's proposed orbital combat stations hint at the direction this technology is heading. But the implications go beyond just defense. Orbital platforms could also serve as hubs for international collaboration, where nations share data and resources to enhance global security. By pooling expertise and technology, countries could create a unified defense network that deters aggression and promotes stability. However, this vision isn't without challenges. The cost of deploying and maintaining these platforms would be astronomical, and questions about sovereignty and control would need to be addressed. Still, the potential benefits: faster response times, reduced collateral damage, and a more secure world make this a future worth pursuing. As we move forward, the development of orbital defense platforms could fundamentally change how nations approach security, shifting the focus from reactive measures to proactive, space-based solutions. And with each technological breakthrough, we edge closer to a future where the skies above are not just a frontier for exploration, but a shield for humanity. Now, shifting our focus to the next frontier in space-based defense, let's explore the potential of space-based laser systems. These advanced systems could revolutionize missile defense by offering a level of precision and speed that ground-based systems simply cannot match. Imagine a scenario where a missile is launched, and within moments, a laser beam from orbit neutralizes it before it can pose a threat. This isn't science fiction, it's a future that could be closer than we think. One of the most significant advantages of space-based lasers is their ability to bypass the limitations of Earth's atmosphere. ground-based lasers often struggle with atmospheric distortion, which can weaken or scatter the beam, reducing its effectiveness. In space, however, lasers can operate with near-perfect accuracy, delivering concentrated energy to their targets without interference. This makes them ideal for intercepting fast-moving threats like hypersonic missiles, which are notoriously difficult to counter with traditional methods. Another key benefit is their global coverage. Unlike ground-based systems, which are tied to specific locations, space-based lasers can be positioned to monitor and protect vast areas of the planet. A single satellite equipped with a laser system could defend multiple regions simultaneously, providing a cost-effective solution for global security. Additionally, these systems could be integrated with other space-based technologies, such as early warning satellites, to create a seamless defense network that detects and neutralizes threats in real time. However, deploying and maintaining space-based laser systems comes with its own set of challenges. The energy requirements for these systems are immense, requiring advanced power sources like solar arrays or nuclear reactors. Keeping the lasers operational in the harsh environment of space also demands robust engineering to withstand radiation, micrometeoroids, and extreme temperatures. Moreover, the cost of launching and maintaining these systems in orbit is a significant hurdle, requiring substantial investment and international cooperation. Despite these challenges, the potential of space-based laser systems is undeniable. They represent a leap forward in defense technology, offering a proactive approach to global security that could deter aggression and save lives. As research and development continue, we may soon see these systems become a cornerstone of space-based defense, transforming the way we protect our planet from emerging threats. Looking ahead, the integration of space-based lasers with other defense technologies could pave the way for a new era of security, where the skies above are not just a domain of exploration, but a shield against the dangers of tomorrow. Now, turning our attention to one of the most pressing challenges in modern defense, let's dive into the role of space-based systems in intercepting hypersonic missiles. These missiles, capable of traveling at speeds exceeding 5 times the speed of sound, are a game-changer in modern warfare. Their speed, combined with unpredictable flight paths, makes them nearly impossible to counter using traditional ground-based systems. This is where space-based defense systems could step in to level the playing field. Hypersonic missiles are designed to evade detection and interception by flying at extremely high altitudes and maneuvering unpredictably. Ground-based radar systems often struggle to track them effectively, leaving little time to respond. However, space-based systems, equipped with advanced sensors and tracking capabilities, could provide a critical advantage. Satellites in orbit can monitor vast areas of the Earth's surface continuously, offering early detection and real-time tracking of these high-speed threats. Once detected, space-based interceptors, such as kinetic kill vehicles or directed energy weapons, could be deployed to neutralize the missile before it reaches its target. One of the most promising technologies for this purpose is the use of space-based lasers. These lasers could deliver precise, high-energy beams to disable or destroy hypersonic missiles in flight. Unlike ground-based systems, space-based lasers are not hindered by atmospheric interference, allowing them to maintain accuracy over long distances. Additionally, their ability to engage multiple targets in rapid succession makes them a formidable tool against swarms of hypersonic missiles, which could be deployed to overwhelm traditional defenses. However, intercepting hypersonic missiles from space is not without its challenges. The sheer speed of these missiles requires extremely fast response times, leaving little room for error. Space-based systems must be capable of processing data and executing commands in milliseconds to effectively neutralize the threat. This demands cutting-edge artificial intelligence and machine learning algorithms to analyze incoming data and make split-second decisions. Furthermore, the energy requirements for space-based interceptors are immense, necessitating advanced power generation and storage solutions to keep these systems operational. Another significant hurdle is the cost and complexity of deploying and maintaining space-based defense systems. Launching satellites into orbit is expensive, and ensuring their reliability in the harsh environment of space adds another layer of difficulty. International collaboration and shared resources could help mitigate these challenges, but political and logistical barriers often complicate such efforts. Despite these obstacles, the potential impact of space-based hypersonic missile interception on global military strategies is profound. By providing a reliable means of countering these advanced threats, space-based systems could deter aggression and stabilize geopolitical tensions. Nations with access to such technology would gain a significant strategic advantage, potentially reshaping the balance of power on a global scale. As we look to the future, the integration of space-based systems with other defense technologies could create a multi-layered shield capable of addressing a wide range of threats. From hypersonic missiles to ballistic projectiles, the skies above may soon become the first line of defense, ensuring the safety and security of nations worldwide. The race to develop these capabilities is already underway, and the implications for global security are nothing short of transformative. Now, shifting our focus to a concept that feels like it's straight out of a sci-fi movie, let's explore the fascinating world of satellite swarm defense. Imagine hundreds or even thousands of small satellites working together in perfect harmony, like a well-coordinated team to protect against potential threats. This is the essence of satellite swarm defense, a revolutionary approach that could redefine how we think about space-based security. Satellite swarms operate on the principle of numbers and coordination. Instead of relying on a single, large satellite, which could be a prime target for adversaries, a swarm consists of numerous smaller satellites that work collectively to achieve a common goal. This approach offers several key advantages. First, it creates redundancy. If one satellite in the swarm is disabled or destroyed, the others can continue to function, ensuring that the system remains operational. This makes satellite swarms incredibly resilient and difficult to neutralize completely. Another major benefit is their ability to overwhelm enemy systems. A swarm can deploy a variety of tactics such as jamming communications, confusing radar systems, or even physically obstructing the path of hostile satellites or missiles. By saturating the battlefield with multiple targets, satellite swarms can force adversaries to divide their attention and resources, making it harder for them to mount an effective counterattack. This concept, often referred to as swarm intelligence, allows the satellites to adapt to evolving threats in real time, learning and adjusting their strategies as the situation unfolds. The adaptability of satellite swarms is perhaps their most impressive feature. Equipped with advanced artificial intelligence, these satellites can communicate with each other, share data, and make collective decisions without human intervention. For example, if one satellite detects an incoming missile, it can instantly relay that information to the rest of the swarm, enabling them to coordinate a response. This level of autonomy and coordination is crucial in high-stakes scenarios where every second counts. However, deploying and managing satellite swarms is not without its challenges. One of the primary concerns is the risk of creating space debris. With so many satellites operating in close proximity, the potential for collisions increases, which could generate dangerous debris fields that threaten other space assets. To mitigate this risk, engineers are developing advanced collision avoidance systems and protocols to ensure the safe operation of satellite swarms. Another challenge is the cost and complexity of launching and maintaining such a large number of satellites. While smaller satellites are generally less expensive to produce than their larger counterparts, the sheer volume required for a swarm can still add up. Additionally, ensuring reliable communication and coordination among the satellites demands cutting-edge technology and robust infrastructure. Despite these hurdles, the potential applications of satellite swarm defense are vast. Beyond military uses, swarms could be employed for disaster monitoring, environmental tracking, and even space exploration. Their versatility and resilience make them a valuable asset in an increasingly complex and unpredictable world. As we look ahead, the development of satellite swarm technology could mark a significant shift in how we approach defense and security in space. By leveraging the power of numbers, adaptability, and artificial intelligence, these swarms could provide a formidable line of defense against a wide range of threats, ensuring that we stay one step ahead in the ever-evolving landscape of space-based warfare. The future of satellite swarm defense is not just about protecting assets in orbit, it's about reimagining the very nature of security in the cosmos. Now, let's turn our attention to a realm where the battlefield is invisible yet incredibly powerful: space-based cyber warfare. In an era where digital threats are as real as physical ones, the role of space-based systems in cyber warfare is becoming increasingly critical. Imagine a scenario where satellites are not just tools for communication or surveillance, but also weapons in a high-stakes game of digital dominance. Space-based cyber warfare revolves around the ability to hack, disrupt, or protect satellites and other space infrastructure. One of the most significant threats in this domain is the potential for adversaries to hack into enemy satellites. A compromised satellite could be used to intercept sensitive communications, manipulate data, or even disable critical systems. For example, a hacked navigation satellite could provide false coordinates, leading to disastrous consequences for military operations or civilian transportation. Another key aspect of space-based cyber warfare is the disruption of communications. Satellites play a vital role in global communication networks, and disrupting these systems can have far-reaching impacts. By jamming signals or launching cyber attacks on communication satellites, adversaries can sever lines of communication, creating chaos and confusion. This tactic could be particularly effective in wartime, where real-time communication is essential for coordinating operations. On the flip side, space-based systems also offer powerful tools for protecting critical infrastructure. Satellites equipped with advanced cybersecurity measures can detect and neutralize cyber threats before they cause harm. For instance, a satellite with robust encryption and intrusion detection systems can safeguard sensitive data and prevent unauthorized access. Additionally, space-based systems can monitor for unusual activity in orbit, such as unauthorized attempts to access or interfere with satellites, providing an early warning system for potential cyber attacks. One of the most intriguing developments in this field is the concept of cyber shields in space. These systems would act as a protective barrier, defending satellites and other space assets from cyber threats. By deploying a network of satellites dedicated to cybersecurity, nations could create a resilient defense system capable of withstanding sophisticated attacks. This approach would not only protect military assets, but also ensure the stability of civilian infrastructure, such as GPS and weather monitoring systems. However, the challenges of space-based cyber warfare are significant. The vast distances and complex environments of space make it difficult to detect and respond to cyber threats in real time. Additionally, the rapid advancement of cyber attack techniques means that defense systems must constantly evolve to stay ahead of potential threats. This requires ongoing investment in research and development, as well as international cooperation to establish norms and protocols for space-based cybersecurity. As we look to the future, the role of space-based systems in cyber warfare will only grow in importance. The ability to hack, disrupt, and protect satellites will be a key factor in determining the balance of power in space. By leveraging advanced technologies and innovative strategies, nations can secure their space assets and maintain a strategic advantage in this new frontier of warfare. The stakes are high, but so are the opportunities for those who can master the art of space-based cyber defense. Now, shifting our focus to the skies above, let's explore the fascinating world of autonomous space drones. These advanced machines are poised to revolutionize how we approach surveillance, reconnaissance, and even defense in the vast expanse of space. Unlike traditional satellites, which are often limited in their maneuverability and functionality, autonomous drones offer unparalleled flexibility and adaptability. One of the most significant advantages of autonomous space drones is their ability to operate independently without constant human intervention. Powered by artificial intelligence, these drones can make real-time decisions based on the data they collect, allowing them to respond swiftly to emerging threats or changing conditions. For instance, a drone equipped with advanced sensors could detect an incoming missile, analyze its trajectory, and deploy countermeasures, all within seconds. This level of autonomy not only enhances efficiency but also reduces the risk of human error in high-pressure situations. In the realm of surveillance, autonomous drones offer a game-changing advantage. They can be deployed to monitor vast areas of space, tracking the movements of satellites, space debris, or even potential adversaries. With their ability to maneuver and reposition themselves, these drones can provide continuous, high-resolution coverage of critical regions. This capability is particularly valuable for monitoring activities in geostationary orbit, where satellites remain fixed relative to the Earth's surface, making them prime targets for interference or attack. Reconnaissance is another area where autonomous space drones excel. Equipped with advanced imaging and sensing technologies, these drones can gather detailed intelligence on enemy assets, infrastructure, or activities in space. For example, a drone could be sent to inspect a suspicious satellite, capturing high-resolution images and analyzing its components to determine its purpose. This information could then be relayed back to command centers, enabling informed decision-making and strategic planning. The integration of artificial intelligence further amplifies the effectiveness of these drones. AI algorithms can process vast amounts of data in real time, identifying patterns, anomalies, or potential threats that might otherwise go unnoticed. Machine learning capabilities allow these systems to improve over time, becoming more adept at recognizing and responding to new challenges. This continuous evolution ensures that autonomous drones remain at the cutting edge of space-based defense technology. However, the rise of autonomous space drones also raises important questions about control and accountability. As these systems become more independent, ensuring they operate within ethical and legal boundaries becomes crucial. There is also the risk of adversaries developing counter-drone technologies, creating a new arms race in space. Addressing these challenges will require international cooperation and the establishment of clear guidelines for the use of autonomous systems in space. Looking ahead, the potential of autonomous space drones is immense. From enhancing surveillance and reconnaissance to providing a robust defense against emerging threats, these systems represent a significant leap forward in space-based technology. As artificial intelligence continues to advance, the capabilities of these drones will only grow, reshaping the future of space defense and opening up new possibilities for exploration and security. The era of autonomous space drones is just beginning, and its impact will be felt across the cosmos. Now, turning our attention to a topic that sparks both fascination and concern, let's delve into the concept of space-based nuclear deterrence. The idea of deploying nuclear weapons in space is undeniably controversial, yet it represents a significant shift in how nations might approach global security in the future. Imagine a scenario where nuclear capabilities are no longer confined to Earth but extend into the vastness of space, fundamentally altering the dynamics of deterrence and warfare. The primary argument for space-based nuclear deterrence lies in its potential to create a more robust and far-reaching defense system. By positioning nuclear weapons in orbit, nations could theoretically neutralize threats from any direction, including intercontinental ballistic missiles launched from Earth. This capability could serve as a powerful deterrent, discouraging adversaries from initiating attacks due to the overwhelming and immediate response such a system could deliver. However, the very nature of this concept raises profound ethical and strategic questions. One of the most pressing concerns is the risk of escalation. Placing nuclear weapons in space could trigger an arms race as nations rush to develop and deploy their own orbital arsenals. This competition could destabilize global security, creating a precarious balance where any miscalculation or technical failure could have catastrophic consequences. Additionally, the deployment of nuclear weapons in space introduces new challenges for arms control treaties, many of which were designed during a time when such technologies were purely speculative. Ethically, the idea of space-based nuclear deterrence is fraught with dilemmas. Space is often regarded as a shared domain, belonging to all of humanity rather than any single nation. Introducing weapons of mass destruction into this environment could be seen as a violation of this principle, potentially sparking international outrage and conflict. Furthermore, the long-term environmental impact of nuclear detonations in space remains uncertain, with the potential to create hazardous debris fields or disrupt satellite networks critical to global communication and navigation. Despite these challenges, proponents argue that space-based nuclear deterrence could enhance global stability by providing a more reliable and immediate response to threats. For instance, a space-based system could intercept incoming missiles before they reach their targets, reducing the likelihood of large-scale destruction on Earth. This capability might also encourage nations to pursue diplomatic solutions, knowing that any aggressive action could be swiftly countered. As we consider the future of space-based nuclear deterrence, it's clear that this concept sits at the intersection of technological innovation, ethical debate, and geopolitical strategy. While the potential benefits are significant, the risks and implications demand careful consideration. The path forward will require not only technological advancements but also international cooperation and a commitment to preserving the peaceful use of space. The question remains, will humanity choose to weaponize the stars, or will we find a way to protect our planet without extending our conflicts beyond its atmosphere? Now, shifting our focus to a less conventional but equally intriguing aspect of space-based defense, let's explore the concept of using space debris as a weapon. While it might sound like something out of a science fiction movie, the idea of weaponizing space debris is a topic that has garnered serious attention in recent years. With thousands of defunct satellites, spent rocket stages, and other fragments orbiting Earth, the potential to turn this debris into a strategic tool raises both fascinating possibilities and significant concerns. The primary appeal of space debris as a weapon lies in its sheer abundance and unpredictability. Imagine a scenario where a nation deliberately targets or manipulates existing debris to collide with an adversary's satellites. Such an attack could disrupt critical communication, navigation, or surveillance systems without the need for traditional weapons. The debris, traveling at incredibly high speeds, could cause catastrophic damage upon impact, effectively disabling or destroying targeted assets. This approach offers a form of asymmetric warfare, where even smaller nations with limited resources could potentially challenge more technologically advanced adversaries. However, the risks associated with weaponizing space debris are immense. One of the most pressing concerns is the creation of uncontrollable debris fields. A single collision in orbit can generate thousands of new fragments, each capable of causing further damage. This phenomenon, known as the Kessler syndrome, could lead to a cascading effect where the density of debris in low Earth orbit becomes so high that it renders space activities nearly impossible. The resulting debris field would not only threaten military and civilian satellites but also endanger future space missions, including those aimed at exploration or scientific research. From a legal standpoint, the weaponization of space debris presents a complex challenge. Current international treaties, such as the Outer Space Treaty of 1967, prohibit the placement of weapons of mass destruction in space, but do not explicitly address the use of debris as a weapon. This legal gray area leaves room for interpretation and potential exploitation. Additionally, attributing responsibility for a debris-based attack could prove difficult, as the origins of specific fragments are often hard to trace. This ambiguity could complicate diplomatic efforts to hold perpetrators accountable and deter future incidents. Despite these challenges, the idea of using space debris as a weapon underscores the growing importance of space as a domain of conflict. It also highlights the urgent need for international cooperation to address the issue of space debris. Efforts to develop technologies for debris removal and mitigation are already underway, but these initiatives must be accelerated to prevent the weaponization of debris from becoming a reality. Furthermore, updating existing treaties to explicitly prohibit such actions could help maintain the peaceful use of space and reduce the risk of escalation. As we consider the future of space-based defense, the potential use of space debris as a weapon serves as a stark reminder of the dual-edged nature of technological advancement. While it offers new avenues for strategic advantage, it also poses significant risks that could have far-reaching consequences for humanity's ability to explore and utilize space. The question we must ask ourselves is whether we can find ways to protect our interests without turning the very environment we rely on into a battlefield. Now, turning our attention to a critical component of space-based defense, let's delve into the role of early warning systems in space. These systems are the first line of defense against a range of threats, from missile launches to asteroid impacts, and their importance cannot be overstated. By detecting dangers early, they provide nations with the precious time needed to respond effectively, potentially saving lives and preventing catastrophic damage. Early warning systems in space operate by continuously monitoring the Earth and its surroundings for signs of potential threats. For example, satellites equipped with advanced sensors can detect the heat signatures of missile launches almost instantly, even before the missiles leave the atmosphere. This real-time data is relayed to ground stations where it is analyzed and used to inform decision-makers. Similarly, these systems can track near-Earth objects such as asteroids or comets that could pose a risk to our planet. By identifying these threats early, we can develop strategies to mitigate their impact, whether through deflection missions or evacuation plans. One of the key advantages of space-based early warning systems is their ability to provide global coverage. Unlike ground-based radar systems, which are limited by geography and line of sight, satellites can monitor vast areas of the planet simultaneously. This makes them particularly valuable for detecting threats in remote or hard-to-reach regions. Additionally, space-based systems are less vulnerable to interference or attack, as they operate outside the reach of most conventional weapons. This resilience ensures that they can continue to function even in the midst of a conflict. However, there is always room for improvement. Current early warning systems, while effective, face challenges such as limited resolution and occasional false alarms. Advances in sensor technology could address these issues, enabling more precise detection and reducing the likelihood of errors. For instance, the development of hyperspectral imaging could allow satellites to distinguish between different types of missile launches, providing more detailed information about the nature of the threat. Similarly, the integration of artificial intelligence could enhance the speed and accuracy of data analysis, enabling faster and more informed decision-making. Another area for improvement is the coordination of international efforts. Early warning systems are most effective when they operate as part of a global network, sharing data and resources across borders. By fostering greater collaboration, nations can ensure that no threat goes unnoticed regardless of where it originates. This could involve the creation of shared satellite constellations, joint monitoring centers, or standardized protocols for data sharing. Such initiatives would not only improve the effectiveness of early warning systems, but also promote trust and cooperation among nations. As we look to the future, the importance of space-based early warning systems will only grow. With the increasing militarization of space and the growing threat of natural disasters, these systems will play a vital role in safeguarding our planet. By investing in their development and fostering international collaboration, we can ensure that they remain a cornerstone of global security. The question is not whether we need these systems, but how we can make them even better. And as we continue to explore the possibilities, one thing is clear: the sky is not the limit when it comes to protecting our world. Now, shifting our focus to a groundbreaking frontier in space defense, let's explore the fascinating world of space-based energy weapons. These advanced systems, which include technologies like particle beams and microwave systems, represent a significant leap forward in how we approach defense in the cosmos. Unlike traditional kinetic weapons, which rely on physical projectiles, energy weapons harness the power of directed energy to neutralize threats with precision and speed. Particle beams, for instance, are a type of energy weapon that fires streams of charged or neutral particles at incredibly high speeds. When these particles collide with a target, they can cause significant damage by disrupting its structure or electronics. Imagine a scenario where an enemy satellite is rendered useless in seconds, not by a missile, but by a beam of energy traveling at nearly the speed of light. This capability makes particle beams a formidable tool for disabling hostile assets without creating space debris, a critical consideration in maintaining the sustainability of Earth's orbit. Microwave systems, on the other hand, operate by emitting high-frequency electromagnetic waves that can interfere with or destroy electronic systems. These weapons are particularly effective against drones, missiles, and other targets that rely on sensitive electronics. For example, a space-based microwave weapon could disable an incoming missile's guidance system, causing it to veer off course or self-destruct. This non-lethal approach minimizes collateral damage while still achieving the desired defensive outcome. One of the most compelling advantages of space-based energy weapons is their ability to engage targets almost instantaneously. Unlike traditional weapons, which require time to travel to their destination, energy weapons can strike at the speed of light. This rapid response capability is crucial in scenarios where even a few seconds can make the difference between success and failure. Additionally, energy weapons are highly scalable, meaning they can be adjusted to deliver varying levels of force, from disabling a single component to completely destroying a target. However, the development and deployment of space-based energy weapons are not without challenges. One major hurdle is the immense power required to operate these systems. Generating and storing the necessary energy in space is a complex engineering problem that requires innovative solutions, such as advanced solar arrays or compact nuclear reactors. Another challenge is ensuring the accuracy and reliability of these weapons, as even a slight miscalculation could result in unintended consequences. Despite these obstacles, the potential applications of space-based energy weapons are vast. Beyond their defensive capabilities, they could also be used for offensive operations, such as disabling enemy satellites or disrupting ground-based communications. Moreover, their precision and minimal collateral damage make them an attractive option for missions where avoiding unnecessary destruction is a priority. As we look to the future, the integration of energy weapons into space-based defense systems could redefine the balance of power in space. By combining these technologies with artificial intelligence and advanced sensors, we could create a network of autonomous defense platforms capable of identifying and neutralizing threats in real time. The question is not if these weapons will become a reality, but how quickly we can overcome the technical and ethical challenges they present. And as we continue to push the boundaries of what's possible, one thing is certain: the era of energy-based defense is just beginning. Now, let's turn our attention to a concept that could revolutionize how we manage and respond to threats in space: artificial intelligence-driven command centers. These advanced systems operating from orbit would serve as the brains of space-based defense, coordinating complex operations, analyzing threats, and making split-second decisions with unparalleled precision. Imagine a network of satellites and defense platforms working together seamlessly, guided by artificial intelligence that can process vast amounts of data in real time. This is the future of space-based command and control. At the heart of these AI command centers is their ability to analyze and interpret data faster than any human operator ever could. Picture this: a swarm of enemy drones is detected approaching a critical satellite. Within milliseconds, the AI system assesses the threat, calculates the best course of action, and deploys countermeasures, all without human intervention. This level of speed and accuracy is crucial in an environment where delays can mean the difference between success and catastrophic failure. By leveraging machine learning algorithms, these systems can also adapt to new threats, improving their effectiveness over time. One of the most significant advantages of AI-driven command centers is their ability to coordinate multiple defense systems simultaneously. For instance, they could manage a fleet of autonomous drones, direct energy weapons, and anti-satellite systems, all while monitoring the broader space environment for emerging threats. This integrated approach ensures that every component of the defense network works in harmony, maximizing efficiency and minimizing vulnerabilities. It's like having a highly skilled conductor leading an orchestra, ensuring every instrument plays its part perfectly. However, the development of these AI command centers is not without its challenges. One major concern is the potential for cyber attacks. If an adversary were to hack into the system, they could disrupt operations or even turn the defense network against its own assets. To mitigate this risk, robust cybersecurity measures must be implemented, including advanced encryption and real-time threat detection. Additionally, there are ethical considerations surrounding the use of AI in decision-making, particularly when it comes to the use of force. How much autonomy should these systems have, and who is ultimately responsible for their actions? Despite these challenges, the potential benefits of AI-driven command centers are immense. They could enhance our ability to respond to threats in space, reduce the risk of human error, and provide a level of coordination that is simply unattainable with current systems. Moreover, as artificial intelligence continues to evolve, these command centers could become even more sophisticated, capable of predicting threats before they materialize and taking preemptive action to neutralize them. As we look to the future, the integration of artificial intelligence into space-based defense systems represents a significant step forward in our ability to protect critical assets and maintain stability in orbit. By combining cutting-edge technology with strategic foresight, we can create a defense network that is not only reactive but also proactive, capable of anticipating and countering threats before they escalate. The question is no longer whether we can achieve this vision, but how quickly we can make it a reality. And as we continue to push the boundaries of innovation, one thing is clear: the era of AI-driven space defense is on the horizon. Now, shifting our focus to a critical aspect of space-based defense, let's explore the evolution of anti-satellite weapons and their growing role in modern warfare. Anti-satellite weapons, often referred to as ASAT, have been a part of military strategy for decades, but their capabilities and significance have dramatically evolved. Initially, these weapons were designed to target and destroy enemy satellites, disrupting communication, navigation, and surveillance capabilities. However, as space has become increasingly vital to global security, the development of more advanced and precise anti-satellite systems has accelerated. The earliest anti-satellite weapons were relatively crude, relying on missiles launched from the ground to physically collide with or explode near their targets. These systems were effective but limited in scope, often creating dangerous debris fields that posed risks to other satellites and spacecraft. Over time, technological advancements have led to more sophisticated methods, such as directed energy weapons and cyber-based systems capable of disabling satellites without causing physical destruction. These newer approaches offer greater precision and reduce the risk of collateral damage, making them more appealing in an era where space is crowded with both military and civilian assets. In modern warfare, anti-satellite weapons play a pivotal role in gaining strategic advantage. By targeting an adversary's satellites, a nation can cripple their ability to gather intelligence, coordinate military operations, and maintain communication networks. This capability is particularly significant in conflicts where space-based assets are integral to command and control. For example, disabling a satellite responsible for guiding precision-guided munitions could severely hamper an enemy's ability to conduct effective strikes. As a result, anti-satellite weapons have become a key component of asymmetric warfare, allowing smaller nations to challenge more technologically advanced adversaries. However, the rise of anti-satellite weapons has also spurred the development of countermeasures. Space-based defense systems are now being designed to detect, track, and neutralize these threats before they can cause harm. One promising approach involves the use of satellite swarms, which can overwhelm an incoming ASAT weapon by presenting multiple targets or physically intercepting it. Another strategy leverages advanced sensors and artificial intelligence to identify and respond to threats in real time, enabling preemptive action. Additionally, some systems are being developed to repair or shield satellites from attacks, ensuring their continued operation even under hostile conditions. The interplay between anti-satellite weapons and space-based defense systems is shaping the future of warfare in orbit. As nations continue to invest in these technologies, the balance of power in space will depend on who can outmaneuver whom in this high-stakes game of cat and mouse. The challenge lies not only in developing effective countermeasures, but also in establishing international norms to prevent the weaponization of space from spiraling out of control. After all, the consequences of unchecked conflict in orbit could extend far beyond military outcomes, threatening the very infrastructure that underpins our modern way of life. As we look ahead, the evolution of anti-satellite weapons and their countermeasures will undoubtedly remain a focal point of space-based defense strategies. The ability to protect critical assets while neutralizing threats will be essential for maintaining stability in an increasingly contested domain. And as technology continues to advance, the line between offense and defense in space will blur, requiring innovative solutions and a proactive approach to safeguarding the final frontier. Now, turning our attention to another critical development in space-based defense, let's delve into the expansion of surveillance networks in orbit. These networks represent a significant leap in our ability to monitor global activities, offering unprecedented levels of insight and control. Space-based surveillance systems are no longer limited to tracking military movements or natural disasters. They now play a central role in everything from environmental monitoring to counterterrorism efforts. By leveraging advanced sensors, high-resolution imaging, and real-time data transmission, these networks provide a bird's-eye view of the planet, enabling governments and organizations to respond swiftly to emerging threats. One of the most remarkable aspects of space-based surveillance is its ability to cover vast areas with incredible precision. Satellites equipped with high-resolution cameras and infrared sensors can detect minute changes on the Earth's surface, from the movement of military vehicles to the growth of illegal crops. This capability is particularly valuable in conflict zones, where real-time intelligence can mean the difference between success and failure. For example, surveillance satellites have been instrumental in monitoring troop movements, identifying hidden infrastructure, and even predicting potential flashpoints before they escalate into full-blown crises. Beyond military applications, space-based surveillance networks are also transforming how we address global challenges. Climate change monitoring, disaster response, and resource management all benefit from the data these systems provide. Satellites can track deforestation, measure sea level rise, and monitor the spread of wildfires, offering critical insights that inform policy decisions and emergency responses. In the aftermath of natural disasters, they can quickly assess damage, identify areas in need of aid, and coordinate relief efforts more effectively than ever before. However, the growing capabilities of space-based surveillance also raise significant privacy concerns. As these networks become more sophisticated, the line between public safety and individual privacy grows increasingly blurred. High-resolution imaging and advanced data analytics can potentially be used to monitor individuals, track their movements, and even predict their behavior. This level of surveillance has sparked debates about the ethical implications of such technologies, particularly in democratic societies where privacy is a fundamental right. Critics argue that without proper oversight, these systems could be misused for mass surveillance, eroding civil liberties and creating a chilling effect on free expression. To address these concerns, some nations and organizations are advocating for the establishment of international regulations governing the use of space-based surveillance. These regulations would aim to strike a balance between leveraging the benefits of these technologies and protecting individual privacy. For instance, guidelines could limit the resolution of images captured over civilian areas or require transparency about how surveillance data is collected and used. Such measures would help ensure that space-based surveillance networks are used responsibly without compromising the rights and freedoms of individuals. As we look to the future, the expansion of space-based surveillance networks will continue to shape the way we understand and interact with our world. These systems offer immense potential for enhancing security, addressing global challenges, and improving decision-making. Yet, they also underscore the need for careful consideration of the ethical and societal implications of their use. By fostering a dialogue between technologists, policymakers, and the public, we can harness the power of space-based surveillance while safeguarding the values that define our societies. This delicate balance will be key to ensuring that these technologies serve as tools for progress rather than instruments of control. Now, shifting our focus to a more tactical aspect of space-based defense, let's explore the concept of space-based communication jamming. This technology represents a powerful tool in modern warfare, capable of disrupting enemy communications and tipping the scales in strategic conflicts. By deploying satellites equipped with advanced jamming systems, nations can effectively neutralize an adversary's ability to coordinate operations, gather intelligence, or even maintain basic command and control. The implications of such capabilities are profound, reshaping the dynamics of both conventional and asymmetric warfare. At the heart of space-based communication, jamming lies a suite of sophisticated technologies designed to interfere with radio frequencies, satellite signals, and other forms of wireless communication. These systems can emit targeted bursts of electromagnetic energy, overwhelming enemy receivers and rendering their communication channels unusable. Unlike ground-based jamming systems, which are limited by geography and line-of-sight constraints, space-based jammers operate from orbit, providing global coverage and the ability to target multiple regions simultaneously. This makes them particularly effective in large-scale conflicts or when dealing with adversaries spread across vast distances. One of the key advantages of space-based jamming is its ability to disrupt critical military operations without the need for direct engagement. For instance, during a conflict, jamming satellites could disable an enemy's radar systems, leaving them blind to incoming threats. They could also interfere with drone communications, grounding entire fleets of unmanned aerial vehicles. Even more strategically, these systems could target an adversary's command centers, severing the flow of information between leadership and frontline troops. Such disruptions can create chaos, delay responses, and ultimately weaken an enemy's ability to mount an effective defense or counterattack. Beyond military applications, space-based communication jamming also has significant implications for cyber warfare. In an era where digital networks are integral to both civilian and military infrastructure, the ability to disrupt these networks from space offers a new dimension of strategic leverage. For example, jamming satellites could interfere with an adversary's internet connectivity, crippling their ability to conduct cyber operations or even maintain essential services. This dual-use capability underscores the versatility of space-based jamming systems, making them a valuable asset in both kinetic and non-kinetic conflicts. However, the deployment of space-based jamming technologies is not without challenges. One major concern is the potential for collateral damage. Since jamming signals can affect a wide range of frequencies, there is a risk of inadvertently disrupting civilian communications, such as emergency services or global navigation systems. This raises ethical and legal questions about the responsible use of such technologies, particularly in densely populated or politically sensitive regions. Additionally, adversaries may develop countermeasures such as frequency hopping or encrypted communications to mitigate the effects of jamming. These factors highlight the need for continuous innovation and adaptability in the design and deployment of space-based jamming systems. Looking ahead, the strategic advantages of space-based communication jamming are likely to drive further investment and development in this field. As nations seek to gain an edge in an increasingly contested space domain, these systems will play a pivotal role in shaping the future of warfare. Yet, their use must be carefully balanced with considerations of international law, ethical responsibility, and the potential for unintended consequences. By fostering collaboration between technologists, policymakers, and military strategists, we can ensure that space-based jamming technologies are employed in ways that enhance security without compromising global stability. As we move forward, the integration of space-based communication jamming into broader defense strategies will continue to evolve, offering new possibilities for deterrence and conflict resolution. This technology not only underscores the growing importance of space in modern warfare, but also highlights the need for thoughtful governance and innovation to harness its potential responsibly. With that in mind, let's now turn our attention to another groundbreaking development in space-based defense: the concept of space-based missile shields and their role in protecting entire regions from ballistic threats. Now let's pivot to a concept that could redefine global security: space-based missile shields. Imagine a network of satellites orbiting Earth, designed not just to detect but to intercept and neutralize ballistic missiles before they can reach their targets. This idea, once the stuff of science fiction, is now being seriously considered as a viable defense strategy. The potential to protect entire regions from missile threats is both groundbreaking and complex, raising questions about feasibility, cost, and the broader implications for international security. At its core, a space-based missile shield would rely on a combination of advanced sensors, tracking systems, and interceptors stationed in orbit. These systems would work together to detect missile launches, calculate trajectories, and deploy countermeasures in real time. Unlike ground-based missile defense systems, which are limited by geography and reaction time, space-based shields could offer global coverage and faster response times. This makes them particularly appealing for defending against intercontinental ballistic missiles, which travel at incredible speeds and can strike targets thousands of miles away in a matter of minutes. One of the most significant advantages of space-based missile shields is their ability to intercept missiles during their boost phase, the initial stage of flight when the missile is most vulnerable. By targeting missiles early, these systems could reduce the risk of debris falling on populated areas and minimize the chances of counterattacks. Additionally, space-based interceptors could be equipped with kinetic kill vehicles or directed energy weapons, such as lasers, to neutralize threats without relying on explosive warheads. This precision and versatility make space-based shields a potentially game-changing tool in missile defense. However, the development and deployment of such systems come with substantial challenges. First, there's the issue of cost. Building, launching, and maintaining a network of missile defense satellites would require significant financial investment, likely running into hundreds of billions of dollars. Second, there's the technical complexity. Creating a system that can reliably detect, track, and intercept missiles in the harsh environment of space is no small feat. Factors like orbital mechanics, signal latency, and the sheer speed of ballistic missiles all add layers of difficulty to the equation. Another critical concern is the potential for escalation. Deploying space-based missile shields could be perceived as a threat by other nations, potentially sparking an arms race in space. Adversaries might respond by developing more advanced missiles or anti-satellite weapons, creating a cycle of competition that undermines global stability. Additionally, there are legal and ethical questions to consider. How would such systems be governed? Who decides when and where they can be used? These are complex issues that would require international cooperation and careful diplomacy to address. Despite these challenges, the strategic benefits of space-based missile shields are hard to ignore. For nations facing persistent missile threats, these systems could provide a critical layer of defense, deterring potential aggressors and safeguarding civilian populations. Moreover, as missile technology continues to advance, the need for innovative defense solutions will only grow. Space-based shields represent one possible answer, offering a way to stay ahead of emerging threats while reshaping the future of global security. As we look to the horizon, the idea of space-based missile shields invites us to rethink the boundaries of defense technology. It's a vision that combines ambition with caution, innovation with responsibility. While the road ahead is fraught with challenges, the potential rewards greater security, enhanced deterrence, and a safer world make it a journey worth pursuing. With that in mind, let's now turn our attention to another fascinating frontier in space-based defense: the potential for manipulating weather patterns from orbit and its implications for global security. Now, shifting our focus to a concept that feels almost like science fiction but is increasingly grounded in reality, let's explore the idea of space-based weather control. Imagine a future where satellites orbiting Earth could influence weather patterns, not just for agricultural or environmental purposes, but as a strategic tool for defense. This possibility raises profound questions about the intersection of technology, ethics, and global security. At its core, space-based weather control would involve deploying advanced systems capable of altering atmospheric conditions. These systems could, for example, disperse clouds to clear skies for surveillance operations, create artificial rain to disrupt enemy movements, or even induce droughts to weaken an adversary's infrastructure. The technology behind this could include high-powered lasers, microwave emitters, or even chemical dispersants released into the atmosphere from orbit. While still in its infancy, the concept builds on existing research into weather modification, such as cloud seeding, and pushes it into the realm of space-based applications. One of the most compelling arguments for space-based weather control is its potential to provide a non-lethal yet highly effective means of defense. By manipulating weather, nations could achieve strategic objectives without direct military engagement, reducing the risk of casualties and collateral damage. For instance, creating a storm to delay an enemy's advance or clearing skies to enhance satellite reconnaissance could offer significant tactical advantages. This approach aligns with the growing emphasis on asymmetric warfare, where technology and innovation often outweigh traditional firepower. However, the ethical and environmental implications of such technology are immense. Altering weather patterns on a large scale could have unintended consequences, disrupting ecosystems, agriculture, and even global climate systems. A decision to induce drought in one region, for example, could lead to famine or mass migration, creating humanitarian crises far beyond the intended target. Additionally, the use of weather control as a weapon raises questions about accountability and governance. Who decides when and where to deploy such systems? How do we ensure they are used responsibly and not as tools of oppression or coercion? Another layer of complexity lies in the potential for misuse or accidental harm. Weather systems are interconnected, and a change in one region could trigger a cascade of effects elsewhere. A satellite designed to create rain over a battlefield might inadvertently cause flooding in a neighboring country, sparking international disputes. Moreover, the technology could fall into the wrong hands, enabling rogue states or non-state actors to wield weather as a weapon of terror. These risks underscore the need for robust international agreements and oversight mechanisms to prevent abuse and ensure transparency. Despite these challenges, the strategic potential of space-based weather control is undeniable. For nations seeking to maintain a technological edge, it represents a frontier of defense innovation that could redefine the rules of engagement. Yet, as with any powerful technology, the key lies in balancing ambition with responsibility. The development of such systems must be guided by ethical considerations, environmental stewardship, and a commitment to global cooperation. As we consider the possibilities of space-based weather control, we're reminded of the delicate balance between human ingenuity and the natural world. It's a reminder that the tools we create to protect ourselves must also respect the planet we share. With this in mind, let's now turn to another groundbreaking concept, the role of quantum communication in space-based defense and how it could revolutionize secure military operations. Now, let's venture into the fascinating world of space-based quantum communication, a technology that promises to redefine how we think about secure military operations. Unlike traditional communication methods, which rely on radio waves or fiber optics, quantum communication leverages the principles of quantum mechanics to transmit information in ways that are virtually impossible to intercept or hack. This makes it an ideal tool for space-based defense systems, where secure and reliable communication is absolutely critical. At the heart of quantum communication is the concept of quantum entanglement, a phenomenon where two particles become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. This means that if you encode information into one particle, it can be instantly transmitted to its entangled partner, even if they're on opposite sides of the planet or even in space. For military applications, this could enable real-time, unhackable communication between satellites, ground stations, and command centers, ensuring that sensitive data remains secure from enemy interception. One of the most significant advantages of quantum communication is its inherent security. Traditional encryption methods, while effective, can still be broken with enough computational power. Quantum communication, on the other hand, is based on the laws of physics, making it immune to conventional hacking techniques. If an enemy tries to intercept a quantum signal, the act of observing it would alter the quantum state, immediately alerting the sender and receiver to the breach. This level of security is unparalleled and could give nations a decisive edge in protecting their military communications. Another key benefit is the potential for faster and more reliable data transmission. In space-based defense systems, where milliseconds can make the difference between success and failure, the speed of quantum communication could be a game changer. Satellites equipped with quantum communication technology could relay critical information such as missile launch warnings or surveillance data, almost instantaneously, allowing for quicker decision-making and response times. This could significantly enhance the effectiveness of space-based defense networks, making them more agile and responsive to emerging threats. However, the development of space-based quantum communication is not without its challenges. One major hurdle is the need for highly sensitive equipment to detect and measure quantum states, which can be easily disrupted by environmental factors like cosmic radiation or temperature fluctuations. Additionally, maintaining the stability of quantum entanglement over vast distances in space requires cutting-edge technology and precise engineering. Despite these obstacles, significant progress has already been made, with experiments demonstrating successful quantum communication between satellites and ground stations. The implications of this technology extend far beyond military applications. Quantum communication could also revolutionize global telecommunications, financial systems, and even internet security, creating a new standard for data protection. But in the context of space-based defense, its potential is particularly transformative. By enabling secure, real-time communication across vast distances, quantum communication could help create a more interconnected and resilient defense network, capable of responding to threats with unprecedented speed and precision. As we look to the future, it's clear that quantum communication will play a pivotal role in shaping the next generation of space-based defense systems. Its ability to provide unparalleled security and speed makes it a cornerstone of modern military strategy, offering a glimpse into a future where communication is not just faster, but fundamentally unbreakable. With this in mind, let's now explore another cutting-edge innovation: the development of stealth technology for space-based systems and how it could give nations a critical advantage in the evolving landscape of space defense. Now, let's shift our focus to a technology that could redefine the art of invisibility in space: stealth technology for space-based systems. Imagine a satellite that can evade detection, slipping through the vast expanse of space like a ghost. This isn't science fiction, it's a rapidly advancing field that could give nations a critical edge in the high-stakes arena of space defense. At its core, space-based stealth technology aims to make satellites and other space assets invisible or nearly undetectable to enemy sensors. One of the most promising approaches involves cloaking devices, which use advanced materials and techniques to bend light or other forms of radiation around an object, effectively rendering it invisible. While cloaking technology is still in its early stages, researchers are making significant strides in developing materials that can manipulate electromagnetic waves, including radar and infrared signals, to hide objects from detection. Another key component of space-based stealth is the use of radar-absorbing materials. These materials are designed to absorb or scatter incoming radar waves, reducing the likelihood that a satellite will be detected by ground-based or space-based radar systems. By coating satellites with these materials, nations can significantly lower their visibility to enemy surveillance, making it harder for adversaries to track or target them. This is particularly important in a world where anti-satellite weapons are becoming increasingly sophisticated. But why is stealth so crucial in space? The answer lies in the growing militarization of space. As more nations deploy satellites for surveillance, communication, and defense, the ability to hide these assets from potential threats becomes a top priority. A stealthy satellite could gather intelligence, relay communications, or even deploy defensive measures without being detected, giving its operators a significant strategic advantage. In a conflict scenario, the ability to operate undetected could mean the difference between mission success and catastrophic failure. However, developing stealth technology for space is no easy task. Space presents unique challenges such as extreme temperatures, radiation, and the vacuum environment, which can affect the performance of stealth materials and systems. Additionally, maintaining stealth over long periods requires constant innovation to stay ahead of detection technologies, which are also advancing rapidly. Despite these challenges, the potential rewards are immense, driving significant investment and research in this field. Looking ahead, the integration of stealth technology into space-based defense systems could revolutionize how nations protect their assets in orbit. By combining cloaking devices, radar-absorbing materials, and other advanced techniques, future satellites could operate with near-perfect invisibility, making them incredibly difficult to detect, track, or destroy. This would not only enhance the survivability of space assets, but also create new possibilities for covert operations and strategic advantage. As we continue to explore the future of space-based defense, it's clear that stealth technology will play a pivotal role in shaping the next generation of military capabilities. Its potential to provide invisibility and protection in the harsh environment of space makes it a cornerstone of modern defense strategies, offering a glimpse into a future where the unseen becomes the ultimate weapon. With this in mind, let's now turn our attention to another critical aspect of space defense: the protection of space-based resources and how defense systems could safeguard humanity's growing presence in orbit. Now let's pivot to a topic that's as vast as space itself: the protection of space-based resources. As humanity's ambitions extend beyond Earth, the need to safeguard valuable assets in orbit and beyond becomes increasingly critical. From mining operations on asteroids to the extraction of rare minerals, space-based resources hold the potential to fuel future technologies and economies. But with great opportunity comes great risk, and defense systems will play a vital role in ensuring these resources remain secure. One of the most promising areas of space resource utilization is asteroid mining. Asteroids are rich in precious metals like platinum, gold, and rare earth elements, which are essential for advanced technologies such as electronics, renewable energy systems, and even space exploration itself. However, the very value of these resources makes them a target for exploitation or sabotage. Without proper protection, mining operations could be disrupted by rival nations, rogue entities, or even cyber attacks, jeopardizing the entire supply chain. This is where space-based defense systems come into play. Imagine a network of satellites and drones specifically designed to monitor and protect mining operations. These systems could provide real-time surveillance, detecting any unauthorized activity or potential threats. Advanced sensors and artificial intelligence could analyze data to identify suspicious behavior, while autonomous defense mechanisms could respond swiftly to neutralize risks. For example, a satellite equipped with non-lethal deterrents, such as directed energy weapons or electromagnetic pulse devices, could disable hostile drones or spacecraft without causing permanent damage. Another layer of protection could involve the creation of secure zones around mining sites. These zones, enforced by space-based defense systems, would act as a buffer against potential threats. Any unauthorized entry into these areas could trigger automated responses, such as jamming communications or deploying countermeasures to deter intruders. This approach would not only safeguard the resources, but also ensure the safety of the personnel and equipment involved in the operations. But the challenges don't end there. Space is a harsh and unpredictable environment, and defense systems must be designed to withstand extreme conditions, from radiation to micrometeoroid impacts. Additionally, the legal and ethical implications of protecting space resources are still being debated. Who has the right to claim and defend these resources? How do we prevent conflicts over ownership? These questions highlight the need for international collaboration and clear regulations to ensure that space resource protection benefits all of humanity, rather than becoming a source of tension. Looking ahead, the integration of defense systems into space-based resource operations could unlock unprecedented opportunities. By securing access to these resources, nations and private companies could accelerate technological advancements, reduce reliance on Earth's dwindling reserves, and even support long-term space colonization efforts. The ability to protect these assets will be a cornerstone of humanity's future in space, ensuring that the wealth of the cosmos is harnessed responsibly and sustainably. As we continue to explore the possibilities of space-based resource protection, it's clear that defense systems will be essential in turning these ambitious visions into reality. The stakes are high, but so are the rewards, offering a glimpse into a future where humanity's reach extends far beyond our planet. With this in mind, let's now turn our attention to another fascinating frontier: the role of space-based systems in detecting and neutralizing biological threats, a topic that could redefine our understanding of defense in the cosmos. Now, shifting our focus to a realm where science fiction meets reality, let's explore the potential of space-based systems to detect and neutralize biological threats. As humanity ventures further into space, the risk of encountering engineered viruses, bioweapons, or even naturally occurring pathogens becomes a growing concern. Space-based biological defense systems could play a pivotal role in safeguarding not only astronauts and space colonies, but also Earth itself from extraterrestrial or man-made biological hazards. Imagine a network of satellites equipped with advanced biosensors, capable of detecting microscopic organisms or harmful agents in space or on planetary surfaces. These sensors could analyze air, water, and soil samples in real time, identifying potential threats before they spread. For instance, a satellite orbiting Mars could monitor the environment for signs of microbial life or contamination, ensuring that any samples brought back to Earth are thoroughly vetted for safety. This level of scrutiny would be crucial in preventing the accidental introduction of alien pathogens to our planet. But detection is only half the battle. Space-based systems could also be designed to neutralize biological threats. One approach involves the use of ultraviolet light or other forms of radiation to sterilize contaminated areas. Satellites equipped with directed energy systems could target and destroy harmful microorganisms on spacecraft, habitats, or even planetary surfaces. Additionally, autonomous drones could deploy disinfectants or other neutralizing agents in affected zones, minimizing the risk of exposure to astronauts or equipment. The implications of space-based biological defense extend beyond space exploration. These systems could also serve as an early warning network for bioweapons launched from Earth. For example, a satellite equipped with advanced sensors could detect the release of engineered viruses or toxins in the atmosphere, providing critical time for governments to respond and mitigate the threat. This dual-purpose capability would make space-based biological defense systems invaluable in both space and terrestrial security. However, developing such systems comes with its own set of challenges. Biological threats are incredibly diverse, ranging from bacteria and viruses to toxins and prions. Creating sensors and neutralization methods that can effectively address this wide array of threats requires cutting-edge technology and interdisciplinary collaboration. Moreover, the ethical considerations of deploying biological defense systems in space must be carefully weighed. Who decides what constitutes a threat? How do we ensure these systems are not misused for harmful purposes? These questions underscore the need for international cooperation and transparent governance. Looking ahead, the integration of space-based biological defense systems could revolutionize our approach to health and security, both on Earth and beyond. By detecting and neutralizing threats before they escalate, these systems could protect humanity from catastrophic outbreaks, whether natural or man-made. They could also pave the way for safer space exploration, enabling us to venture deeper into the cosmos with confidence. As we consider the possibilities of space-based biological defense, it's clear that this technology holds immense potential to safeguard our future. The ability to detect and neutralize threats in space could be a game-changer, ensuring that humanity's journey into the stars is not only ambitious but also safe. With this in mind, let's now turn our attention to another groundbreaking frontier: the use of space-based electromagnetic pulse weapons and their potential to reshape the landscape of modern warfare. Now let's dive into a fascinating yet potentially disruptive technology: space-based electromagnetic pulse weapons. These systems, often referred to as EMP weapons, have the capability to disable or destroy electronic systems over vast areas, making them a powerful tool in modern warfare. But how exactly do they work, and what makes them so strategically significant? At their core, EMP weapons generate a burst of electromagnetic energy that can overload and fry electronic circuits. When deployed in space, these weapons could target satellites, communication networks, or even ground-based infrastructure, effectively crippling an adversary's ability to coordinate military operations or maintain civilian systems. For example, a single EMP burst from a satellite could disrupt everything from missile guidance systems to power grids, leaving an enemy vulnerable and disoriented. The strategic value of space-based EMP weapons lies in their ability to deliver a non-lethal yet devastating blow. Unlike traditional weapons that cause physical destruction, EMPs focus on disabling technology, which can be just as effective in neutralizing a threat. This makes them particularly appealing in scenarios where minimizing casualties is a priority. Imagine a conflict where a space-based EMP weapon disables an enemy's radar and communication systems, rendering their defenses useless without firing a single bullet. The psychological impact alone could be enough to force a swift resolution. However, the use of EMP weapons is not without significant risks. One major concern is collateral damage. Because EMPs affect all electronic systems within their range, they could inadvertently harm neutral or even allied infrastructure. For instance, a weapon designed to target a specific region might also disrupt global communication satellites, affecting everything from GPS navigation to international banking systems. This raises serious ethical and practical questions about the responsible use of such technology. Another challenge is the potential for escalation. If one nation deploys a space-based EMP weapon, it could trigger an arms race with other countries rushing to develop similar or counteractive systems. This could lead to a destabilized global security environment where the threat of EMP attacks becomes a constant concern. Additionally, the development and deployment of these weapons require advanced technology and significant resources, making them accessible only to a handful of nations. This imbalance could further exacerbate geopolitical tensions. Despite these challenges, the potential applications of space-based EMP weapons are hard to ignore. They could serve as a powerful deterrent, discouraging adversaries from engaging in hostile actions by threatening their technological infrastructure. In a world increasingly reliant on electronics, the ability to disrupt an enemy's systems without causing physical harm could redefine the rules of warfare. As we look to the future, the development and regulation of space-based EMP weapons will be critical. Balancing their strategic advantages with the risks they pose will require international cooperation and clear guidelines. The question is not just whether we can build these weapons, but whether we should, and how to ensure they are used responsibly. With this in mind, let's now explore another intriguing aspect of space-based defense: the psychological impact of these technologies and how they could be used to influence the behavior of adversaries. Now, let's shift our focus to a more unconventional yet equally fascinating aspect of space-based defense: psychological warfare. While we often think of military technology in terms of physical destruction or strategic advantage, the ability to influence an adversary's mindset can be just as powerful. Space-based systems open up entirely new possibilities for psychological operations, leveraging the vastness of space to create effects that are as much about perception as they are about technology. One of the most intriguing applications is the use of holographic projections. Imagine a scenario where a satellite in orbit projects a massive, lifelike hologram over a battlefield or a city. This could be used to display intimidating imagery, such as symbols of power or even simulated threats, designed to sow fear and confusion among enemy forces or civilian populations. The psychological impact of seeing a seemingly impossible display in the sky could be enough to disrupt morale and decision-making, potentially altering the course of a conflict without firing a single shot. Another approach involves the disruption of communication and information systems. Space-based platforms could be used to jam or manipulate enemy broadcasts, replacing them with carefully crafted messages designed to demoralize or mislead. For example, a satellite could intercept and alter radio transmissions, spreading false information about troop movements or the status of a battle. This kind of manipulation can create doubt and uncertainty, weakening an adversary's resolve and undermining their ability to coordinate effectively. The psychological effects of space-based systems aren't limited to direct manipulation. The mere presence of advanced space-based defense capabilities can act as a deterrent, influencing an adversary's behavior before any conflict even begins. Knowing that an opponent has the ability to project power from space, whether through holograms, communication jamming, or other means, can create a sense of vulnerability and caution. This psychological edge can be just as valuable as any physical weapon, shaping the strategic landscape in subtle but profound ways. However, the use of space-based psychological warfare raises important ethical questions. Manipulating perceptions and emotions on such a scale could have unintended consequences, potentially escalating conflicts or causing widespread panic. There's also the risk of misuse, where these technologies could be employed to suppress dissent or control populations rather than defend against genuine threats. As with any powerful tool, the challenge lies in ensuring that space-based psychological warfare is used responsibly and in accordance with international norms. Looking ahead, the development of these technologies will likely spark debates about their role in modern warfare. Will they be seen as a humane alternative to physical destruction, or as a new form of coercion that blurs the line between defense and manipulation? The answers to these questions will shape not only the future of space-based defense, but also the ethical framework within which these systems operate. With this in mind, let's now turn our attention to another critical area of space-based defense: the potential for international collaboration in developing and regulating these advanced systems. Now, let's explore a vision of the future where nations come together to address the challenges of space-based defense through international collaboration. As the stakes in space grow higher, the idea of shared systems, treaties, and joint missions becomes not just a possibility but a necessity. Space, after all, is a domain that transcends borders, and the threats it poses, whether from asteroids, hostile actions, or even space debris, are challenges that no single nation can tackle alone. One of the most promising areas for collaboration is the development of shared space-based defense systems. Imagine a network of satellites and platforms operated by multiple countries, each contributing resources and expertise to create a unified shield against threats. These shared systems could include early warning satellites to detect missile launches, orbital platforms for intercepting incoming threats, and even joint research initiatives to advance technologies like directed energy weapons or autonomous defense drones. By pooling resources, nations could achieve capabilities that would be far more effective and cost-efficient than going it alone. Treaties and agreements will also play a crucial role in shaping the future of space-based defense. Just as the Outer Space Treaty of 1967 laid the groundwork for peaceful exploration, new agreements could establish rules for the use of space-based defense systems. These treaties might address issues like the deployment of weapons in space, the protection of critical space infrastructure, and the prevention of conflicts that could escalate into space warfare. International collaboration in drafting and enforcing these agreements will be essential to maintaining stability and preventing an arms race in orbit. Joint missions offer another exciting avenue for cooperation. Picture multinational teams working together on missions to test new defense technologies, monitor space debris, or even respond to potential asteroid threats. These missions could serve as a proving ground for collaborative efforts, building trust and fostering a spirit of shared responsibility. For example, a joint mission to deploy a swarm of satellites for global surveillance could provide real-time data to all participating nations, enhancing security and transparency. However, international collaboration in space-based defense is not without its challenges. Differences in national interests, technological capabilities, and political priorities could create friction. There's also the risk that some nations might seek to dominate or exploit shared systems for their own gain. Overcoming these obstacles will require a commitment to transparency, mutual respect, and a shared vision of space as a global commons. The potential benefits of such collaboration are immense. By working together, nations can reduce the risk of conflict, share the costs and rewards of space-based defense, and ensure that space remains a domain of peace and security. This spirit of cooperation could also extend beyond defense, paving the way for joint efforts in space exploration, resource utilization, and scientific discovery. As we look to the future, the question is not whether international collaboration in space-based defense is possible, but how we can make it a reality. The choices we make today will determine whether space becomes a battlefield or a frontier of unity and progress. With this in mind, let's now turn to another critical aspect of space-based defense: the role of environmental monitoring in ensuring global security. Now, let's shift our focus to a fascinating yet often overlooked aspect of space-based defense: environmental monitoring. While we typically think of defense systems in terms of protecting against human-made threats, space-based technologies also have the potential to safeguard our planet from environmental dangers. By leveraging satellites and advanced sensors, these systems could play a critical role in detecting and responding to climate shifts, natural disasters, and other environmental changes that pose risks to global security. Imagine a network of satellites equipped with high-resolution cameras, thermal sensors, and atmospheric analyzers, constantly scanning the Earth for signs of environmental stress. These systems could detect rising sea levels, melting ice caps, or deforestation in real time, providing early warnings that allow nations to prepare and respond. For example, a satellite monitoring system could identify a rapidly intensifying hurricane days before it makes landfall, giving communities crucial time to evacuate and governments the ability to allocate resources effectively. But the applications go beyond natural disasters. Space-based environmental monitoring could also track human activities that threaten global stability, such as illegal logging, oil spills, or the spread of wildfires. By providing precise, real-time data, these systems could help enforce international environmental agreements and hold nations accountable for their actions. This capability would not only protect ecosystems but also reduce tensions that could arise from resource scarcity or environmental degradation. One of the most promising areas is the use of space-based systems to monitor climate change. Satellites could measure greenhouse gas emissions, track changes in global temperatures, and even predict the long-term impacts of rising carbon levels. This data could inform international policies aimed at mitigating climate change, ensuring that nations work together to address one of the greatest threats to our planet. In this way, space-based defense systems could contribute not just to military security, but to the broader goal of planetary security. However, integrating environmental monitoring into space-based defense systems is not without challenges. The sheer volume of data generated by these systems would require advanced artificial intelligence to process and analyze. There's also the question of how to share this data equitably among nations, ensuring that all countries, regardless of their technological capabilities, can benefit from the insights provided. Overcoming these challenges will require international cooperation, much like the collaborative efforts we discussed earlier. The potential benefits are immense. By using space-based systems to monitor environmental changes, we can not only protect our planet but also prevent conflicts that arise from resource scarcity or environmental disasters. This approach aligns with the broader vision of space as a domain for peace and cooperation, where technology serves not just to defend but to preserve and enhance life on Earth. As we continue to explore the future of space-based defense, it's clear that environmental monitoring represents a vital intersection of security, sustainability, and innovation. With this in mind, let's now turn to our final prediction: the role of human augmentation in shaping the future of space-based defense systems. Now, let's venture into a bold and futuristic concept that could redefine the very nature of defense: human augmentation in space. Imagine a world where soldiers are not just equipped with advanced weapons or protective gear, but are physically and mentally enhanced through cutting-edge space-based technologies. This idea, once confined to the realm of science fiction, is inching closer to reality as advancements in biotechnology, artificial intelligence, and space exploration converge. At the heart of this prediction lies the concept of exoskeletons, wearable robotic systems that amplify human strength, endurance, and agility. In the harsh environment of space, where gravity and atmospheric conditions differ drastically from Earth, exoskeletons could enable soldiers to perform tasks that would otherwise be impossible. Picture a soldier effortlessly lifting heavy equipment or traversing rugged lunar terrain, all while maintaining peak physical performance. These enhancements could be powered by energy systems developed in space, such as solar arrays or compact nuclear reactors, ensuring sustained operation even in the most remote locations. But the potential of human augmentation doesn't stop at physical enhancements. Neural implants, tiny devices integrated into the brain, could revolutionize how soldiers process information and make decisions. By connecting directly to space-based networks, these implants could provide real-time access to vast amounts of data, from satellite imagery to tactical updates. A soldier could instantly analyze enemy movements, predict threats, and coordinate with teammates, all with the speed and precision of a supercomputer. This fusion of human intuition and machine intelligence could create a new breed of defenders, capable of outthinking and outmaneuvering adversaries in ways we can barely imagine today. Another intriguing possibility is the use of genetic engineering to enhance human resilience in space. Scientists could develop modifications that allow soldiers to withstand extreme radiation, prolonged exposure to microgravity, or even the psychological stresses of isolation. These enhancements could be tailored specifically for space-based missions, ensuring that soldiers remain effective and healthy in environments that would otherwise be hostile to human life. Of course, the integration of human augmentation into space-based defense raises significant ethical questions. How far should we go in altering the human body for military purposes? What safeguards would be needed to prevent misuse or unintended consequences? These are complex issues that will require careful consideration as the technology evolves. Yet the potential benefits are undeniable. Enhanced soldiers could perform missions with greater efficiency, reduce the risk of casualties, and even pave the way for new forms of cooperation between humans and machines. As we look to the future, it's clear that human augmentation could play a pivotal role in shaping the next generation of space-based defense systems. By combining the strengths of human creativity and adaptability with the precision and power of advanced technologies, we could unlock capabilities that were once thought impossible. This vision of enhanced defenders operating seamlessly in the vast expanse of space represents not just a leap forward in military strategy, but a profound evolution of what it means to be human. With this in mind, let's now turn to the ethical implications of human augmentation in space-based defense. exploring the challenges and responsibilities that come with such transformative technologies. As we explore the possibilities of human augmentation in space-based defense, it's essential to pause and consider the ethical landscape that comes with such transformative technologies. The idea of enhancing human soldiers with exoskeletons, neural implants, or genetic modifications raises profound questions about the boundaries of human identity, the potential for misuse, and the broader implications for society. One of the most pressing concerns is the risk of dehumanization. When soldiers are augmented to perform beyond natural human limits, there's a danger that they could be viewed more as tools or machines than as individuals. This shift could erode the value placed on human life and dignity, reducing soldiers to mere components of a larger military system. How do we ensure that these enhancements serve to empower individuals rather than strip them of their humanity? This question becomes even more critical in the context of space, where isolation and the harsh environment could amplify feelings of detachment or alienation. Another ethical challenge lies in the potential for inequality. If only certain nations or groups have access to advanced augmentation technologies, it could create a significant imbalance in global power dynamics. Imagine a scenario where one country fields an army of superhuman soldiers, while others are left with conventional forces. This disparity could escalate tensions and lead to a new kind of arms race, one that prioritizes technological dominance over diplomacy and cooperation. The ethical responsibility to ensure fair and equitable access to such technologies cannot be overlooked. The issue of consent also comes into play. Augmentation procedures, especially those involving neural implants or genetic modifications, are irreversible in many cases. Soldiers may face pressure to undergo these enhancements to remain competitive or effective in their roles. But how do we guarantee that their decisions are truly voluntary, free from coercion or undue influence? Ensuring informed consent and protecting the autonomy of individuals will be crucial as these technologies advance. Moreover, the potential for misuse of augmentation technologies is a significant concern. In the wrong hands, these enhancements could be used to create soldiers who are not only physically superior, but also psychologically controlled or manipulated. The integration of artificial intelligence with neural implants, for example, could open the door to scenarios where soldiers' thoughts and actions are influenced or monitored by external systems. This raises alarming questions about privacy, free will, and the potential for abuse by authoritarian regimes or rogue actors. Finally, there's the broader impact on human rights. As we push the boundaries of what it means to be human, we must consider how these changes affect our understanding of rights and freedoms. Will augmented individuals face discrimination or stigma? How do we define and protect the rights of those who are no longer fully human in the traditional sense? These are complex questions that will require careful thought and international collaboration to address. While the potential benefits of human augmentation in space-based defense are undeniable, the ethical challenges are equally significant. As we move forward, it's crucial to establish clear guidelines, oversight mechanisms, and ethical frameworks to ensure that these technologies are developed and used responsibly. By balancing innovation with moral considerations, we can harness the power of human augmentation to enhance security and exploration in space, without compromising the values that define us as a species. With these ethical considerations in mind, let's now turn to the future scenarios where augmented humans could play a pivotal role in space defense, envisioning how these advancements might shape the next frontier of warfare and exploration. Now, let's step into the realm of possibility and explore how augmented humans might redefine the future of space-based defense. Picture this: a team of soldiers equipped with advanced exoskeletons, neural implants, and enhanced sensory capabilities, deployed to protect critical space infrastructure. These augmented individuals could operate in the harsh conditions of space with unparalleled efficiency. their bodies adapted to withstand extreme temperatures, radiation, and microgravity. Their neural implants would allow them to interface directly with spacecraft systems, enabling real-time decision-making and coordination without the delays of traditional communication methods. In this scenario, augmented humans become the ultimate defenders of orbital platforms, ensuring the security of satellites, space stations, and other vital assets. But the role of augmented humans in space defense could extend far beyond physical protection. Imagine a scenario where soldiers with enhanced cognitive abilities are tasked with analyzing vast amounts of data from space-based surveillance networks. Their augmented brains could process information at incredible speeds, identifying potential threats and devising strategies in moments. This capability would be invaluable in a high-stakes environment where every second counts. Augmented humans could also serve as the frontline responders to cyber threats, using their neural interfaces to detect and neutralize attacks on space-based systems before they cause damage. Another fascinating possibility is the use of augmented humans in psychological warfare. Picture a soldier whose neural implants allow them to project holographic illusions or disrupt enemy communications through advanced electromagnetic manipulation. These capabilities could be used to confuse or demoralize adversaries, creating a strategic advantage without the need for direct confrontation. In this way, augmented humans could become not just physical defenders but also psychological operatives, leveraging their enhancements to outmaneuver opponents in the mental battlefield. Of course, the integration of augmented humans into space defense would also raise new challenges. For instance, how do we ensure the loyalty and reliability of these enhanced individuals? With their abilities so closely tied to technology, there's a risk of hacking or manipulation by adversaries. Safeguarding the integrity of neural implants and other augmentations would be a top priority, requiring robust cybersecurity measures and constant vigilance. Additionally, the psychological impact of augmentation on soldiers must be carefully managed. How do we prevent feelings of isolation or detachment in individuals who are no longer fully human in the traditional sense? These are questions that will need to be addressed as we move toward this future. As we look ahead, it's clear that augmented humans could play a transformative role in space-based defense, reshaping the way we think about warfare and exploration. Their unique capabilities would enable us to tackle challenges that are currently beyond our reach, from defending orbital assets to conducting complex missions in deep space. Yet, as with any groundbreaking technology, the path forward must be guided by careful consideration of the ethical, social, and strategic implications. By embracing innovation while upholding our values, we can unlock the full potential of human augmentation to secure a safer and more prosperous future in space. With these possibilities in mind, let's now turn our attention to the broader implications of these advancements, exploring how they might influence global defense strategies and international collaboration in the years to come. As we bring this exploration to a close, it's clear that the future of space-based defense systems is not just a distant dream but a rapidly approaching reality. From orbital defense platforms and space-based lasers to autonomous drones and augmented humans, the 25 predictions we've discussed paint a vivid picture of how technology will redefine global security. These advancements promise to revolutionize the way we protect our planet, assets, and even ourselves, offering unprecedented capabilities to detect, deter, and neutralize threats from above. The potential of these systems to transform global defense strategies is immense. Imagine a world where missile shields in space render ballistic attacks obsolete, where satellite swarms provide unbreakable surveillance, and where quantum communication ensures secure, instantaneous coordination across the globe. These innovations could shift the balance of power, creating new opportunities for collaboration while also raising complex ethical and strategic questions. How do we ensure these technologies are used responsibly? How do we prevent an arms race in space? And how do we balance the need for security with the preservation of peace? As we stand on the brink of this new era, one thing is certain. The future of space-based defense will be shaped not just by technology, but by the choices we make today. The decisions we make about development, deployment, and regulation will determine whether these systems become tools of protection or instruments of conflict. So, what do you think? How should humanity navigate this uncharted territory? Share your thoughts in the comments below. Let's start a conversation about the future of space-based defense and what it means for all of us. Don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss an update on the latest in futuristic technologies and lifestyle. Together, let's explore the possibilities and shape a future that's not only secure but also inspiring.